as we continue talking about our absolute value inequalities and equations, let's take a second to mark our progress and see where we are at. So far, we have been talking about simpler absolute value inequalities and equations. So that means absolute value inequalities and equations where I only have one term that is under my absolute value signs, or I only have a single variable. And because of that, I can easily get rid of my absolute value signs. I can translate this just into usually two algebraic equations that I can just then solve individually without the absolute value signs. And so for these, I can translate these. And so I can usually do these using algebra. Now, as you get into more complex absolute value equations and inequalities, this is going to become harder to do. It is going to become harder to translate, to get rid of your absolute value signs. And that is because when you have two or more terms under your absolute value signs, or you have multiple variables, well, remember, so when you're getting rid of your absolute value signs, you're usually ending up with two scenarios. The scenario where what's under the absolute value sign is greater than zero, then the one where it's less than zero. So once you start having multiple expressions under your absolute value signs, well, now we're talking about we have four possible scenarios. And so it starts getting very crowded on the page. Algebra, it starts becoming the longer approach sometimes in these cases, and it sometimes starts becoming the more confusing and the more complicated approach. So as these get more complex, oftentimes I am finding myself having to resort to testing numbers, or sometimes I am doing a combination algebra and testing numbers, or sometimes I'm really just sitting there having to think about it a bit in my head. So let's take a detour here to talk about testing numbers on the GMAT, particularly testing numbers on data sufficiency questions, because I think that testing numbers is a very useful skill to have on the GMAT. And when people first start out studying, I see a lot of times that they are testing numbers too much. And so especially when people take a diagnostic test, and so they haven't studied at all, and they know that they haven't studied at all, they are basically testing numbers for almost every type of quant question because it is the only thing that they know how to do. However, when people then start studying and they feel like now they do know some stuff, I see people get into this mindset that testing numbers is the wrong approach, that they should always be trying to do things algebraically. And if they are testing numbers, then they are doing something wrong, and therefore they are very hesitant to do it, and they don't really practice their testing number skills. But in my case, I don't always see the algebraic way of doing something. So if I don't know how to do something algebraically, if I cannot translate it, for example, then I sort of have no choice but to test numbers. Other times, testing numbers is quicker, or it is more efficient. And then sometimes it'll be true that you really cannot solve a question algebraically, and testing numbers is really the only way that you can get to the final answer. So I think testing numbers is a very useful skill to have. Really, you want to have multiple ways of doing any question. So testing numbers should always be an option. And I think to limit yourself only to algebra, well, what is even the point of that? Why would you ever want to limit the number of ways that you can do something? So in order to get comfortable testing numbers, you just want to have a framework for doing it so that you can do it in a very deliberate and a very organized way. So this is the framework that I use when I am testing numbers. And again, this is mostly true for data sufficiency. So what I'm trying to do is I imagine that I am designing an experiment. And so just with any science experiment where you always begin with a hypothesis of some sort, when I'm testing numbers on a data sufficiency question, I'm always beginning with the same hypothesis. And that is this. I'm always trying to prove insufficiency. I'm always starting with the hypothesis that this statement is insufficient. And why is that? So here I have these three outlines of data sufficiency questions. And so I didn't include actual statements here because I don't have to. This is just for demonstrative purposes. So I just have a prompt here, and then you can come up with any statement you want, really. So say I just have some prompt that says, what is X? And then I decide that I'm going to do this by testing numbers. So I plug in one number and I get X is equal to 3. And then I plug in some other number for this statement and I get X is equal to 3 again. Then I plug in some other number and again I get X is equal to 3. So at this point, I have 3 numbers that I tested. Every single one of them gave me X is equal to 3. So I would probably say this is sufficient. And then move on to the next statement. But think about what I really did here. I didn't really prove sufficiency. I have just shown, I have not proven that it's sufficient to say X is equal to 3. All I have done is I have shown that for these 3 examples, I got an answer of X is equal to 3. And technically, in order to prove sufficiency, I would have to test every single possible number, plug in every single possible number, of which there are probably infinite possibilities, and I would have to show that for every single one, they give me an output of X is equal to 3. Now that is impossible. What is possible, though, is to prove insufficiency, because to prove insufficiency, I only need 2 values. I only need 2 examples, because once I get a value of X is equal to 3 here, well, if I can then get a second example of X is equal to 2, well, I have now proven insufficiency because I have come up with 2 different values for X and I have proven it. And so what does this mean? So I'm always trying to prove insufficiency. It also means you always need, when you are testing numbers, at least 2 cases. And the first case does not matter. This number here, when I got X is equal to 3, this tells me nothing. It is only once I get to the second case that I can infer something. Because so for the first number that you choose, you just choose whatever the easiest possible number you can think of that fits the criteria of the statement. It will give you some number here. So here it gives us X equal 3. It is the second example that you choose now that matters. Because now, if you are trying to prove insufficiency, you should be trying to plug in, a number that you're trying to maximize the probability of getting something other than a 3. Because you are trying to prove insufficiency. So if you chose a positive integer here, choose a negative integer. Then maybe choose positive fractions. Then maybe choose negative fractions. And then only if no matter how hard you try, after trying positive integers, negative integers, positive fractions, negative fractions, no matter how hard you tried, you kept getting values of X is equal to 3. Then would I say sufficient? But I would also remember that I really have not proven sufficiency. I have just failed to prove insufficiency. And so that is the fourth rule of my framework here. And that is when I select something as sufficient. So usually I say 3 examples is ideal. 4, if you really have the time, would be great. 2 is less than ideal. But if that's all you can do in the time given, that's better than nothing. 1 example really tells you nothing. You really would have been better off just guessing and saving that time. It is not until you get to your second example that you have a chance of proving anything. And then the last thing to keep in mind is you need to know your criteria when you are trying to prove insufficiency. So let's take a look at a different question. So if instead of saying what is X, our question said, is X equal to 3? And then, so again, I plugged in some number and I got X is equal to 2 for my first output. And then I plugged in something else and I got X is equal to 4. Now, if you were still thinking in terms of this question here, you might say, oh, I have proven insufficiency because I've gotten 2 different values for x. But you have to know your criteria, which means knowing what your question is asking. And our question is asking, is x equal to 3? Therefore, what that means is, in terms of answers, there's really only 2 options. There are x is equal to 3, then there is everything else. And so you almost can't think of this as being x is equal to 2 and x is equal to 4. This is really just a no to our question. X is not equal to 3. Then this here is another no. So even though we have 2 different values for x, really what we are on the path of here is we're closer to proving sufficiency because we have 2 outcomes that gave us a no. And so really what we are looking for if we are trying to prove insufficiency is now we want a yes. So if I'm trying to prove insufficiency, now I want to choose a number here that will maximize the likelihood of getting a 3 for x. And so let's say I get that on my 3rd try here. Once I have a no and a yes to my question, well, that satisfies my criteria for insufficiency, and I can stop here. I have proven it. And so let's say I got x is equal to 5 here. So now I have all different values for x, but really this is just further evidence of sufficiency because do not confuse sufficient to say no, which is what this is, with insufficient. And so I at this point, after choosing 3 examples, I would probably say this is sufficient. It's just sufficient to say no to our question. X is not equal to 3. So let's take a look at another example here, this time with inequality. So is x greater than 2 but less than 10? And so for here, let's say I plug in some number and get a value for x of x is equal to 10. So with inequalities, sometimes you have to think about, well, what happens when you get to something that's equal to one of your boundaries? And so here, our question is asking, is x between 2 and 10 non-inclusive? So x is equal to 10 is a no to our question because x is not between 2 and 10. So now I'm trying to prove insufficiency. I am actively trying to get a number that is between 2 and 10. So let's say I choose another number and I get x is equal to 11. Well, this is just another no. So I am on the path to answering sufficient here. And so then let's say I choose another number and I get x is equal to 1. So again, all different values for x, but none of them are between 2 and 10. So this is really, I don't think of this as 3 different values for x. This is just 3 no's to our question. And then only if I have the time and I do I can choose one more example and I get x is equal to 4. Well, now I've proven insufficiency and I can stop. And so only if when I'm choosing sufficiency, it's only because I sort of failed to prove insufficiency. No matter how hard I tried to get a value that was between 2 and 10, I couldn't do it, and I kept getting no's to my question. Or at some point, you will get a value between 2 and 10, and then you can say that you have proven insufficiency. So this is the framework I use. Like I said, you need at least 2 examples. This means, but also means that the first example does not matter. So you can just use the easiest numbers that you can think of that still fit the criteria of your statement. And oftentimes, you can use this in combination with algebra, or maybe sometimes, for example, here, if I get x is equal to 3 for the first example I choose, and then I choose another example and I get x equal to 3 again. Well, sometimes, even though you've only chosen 2 examples, you sort of see the algebra. You see the reason why 3, you keep getting 3 as an outcome. And so when that's happened, that's sort of just as good as having proven algebraically. And so you can say sufficient at that point. The real reason I think I find this helpful is because on data sufficiency, it allows me to reuse information, which is always what you want to be doing. Testing numbers can take a long time, especially on data sufficiency. And so when you are, for example, when you are looking at your statements together, you want to reuse as many of the examples as you can without having to come up with you want to reuse as many examples as you can from having looked at the statements individually. You don't want to have to come up with entirely new examples when you are looking at them together. And so this allows me to do that because I can sort of put all my inputs into a table somewhere. And then when I look at them together, I just need to make sure that I'm only choosing examples that meet the criteria of both statements, but I have a very clear framework. And sometimes I can see that, I can reuse 2 examples between examples I chose for statement 1 and 2 that together make it insufficient, even when looking at them together. And so I don't have to really even do any work when looking at the 2 statements combined. And so I think testing numbers is very useful. I definitely do not think of it as the wrong way of doing something. And whenever I can, I try to see how I try to approach a problem in 2 different ways. When I'm reviewing that question, if I did it algebraically, I try to do it by testing numbers when reviewing, and then I can choose which way works best for me. So we will use this framework in some of the absolute value questions we do coming up.